About previous work in 2D case, and then I will like to talk about the new numerical scheme for the Chernobynsky functional and 3D simulations. So this is a joint work with Carlos Garcia Cervera at UC Santa Barbara. So first, I'm going to introduce the model, previous work, and then the analytical tool that I used is a gamma convergence theory and the bifurcation method. And then numerical simulation for 2D follows, and then I'll talk about the Chernobynsky model that for the smectic crystals, and then I will briefly talk about the analysis in 3D and simulations. So simple model for the pneumatic case, I'm using that one constant approximation for the Osin-Frank pneumatic energy density, and then for the smectic liquid crystals, so we are going to need to introduce this complex order parameter introduced by the Jan. So this, the way I understand this order parameter is this. So if the rho, that's the density, the modulus of the psi, it is 0, then everywhere is a uniform molecular mass density. So we lose the layer density, we lose the layer structure. If rho is 1, then we have a perfect smectic liquid crystal. So, for example, constant, then we have perfect liquid crystal, smectic liquid crystals. But if rho is becomes smaller, then the layer structure is not as clearly as seen as before we had the bigger constant there. So this rho, the modulus of psi, gives the smectic layer density. And this phi, that phase, that gives the location of the layers. So this that level set of phi will describe the layer surface in this case. So obviously we lose the smectic layer density when the modulus psi equals 0. So it goes to the pneumatic phase. If the minimizer for the free energy psi becomes 0. So that's the parameter, and then we combine these two terms. So Fn, that stands for the pneumatic energy density, Fa, smectic A liquid crystal free energy. So this is that covariant energy term, and then this is the phase transition terms. So R is the constant depending on the temperature. So let's assume that we are away from the phase transition to the pneumatic. Then we assume that this is the modulus of psi is constant, then this we can just change that this R over G equals 1. Then under the transformation, so we can see that this is that smectic A energy simple case, and then so this penalizes the phase transition, and the levels of phi are layered. So grad phi, that is the layer normal direction. So when they are parallel to each other with the director, that is with for the smectic A energy case. So directors are perpendicular to the layer, that's the smectic A energy. So then it is going to be minimized when they are parallel to each other. And the Q is like the wave number. So this is the explanation of this free energy. So then it's the schematic picture for the undulation phenomena. So we apply the magnetic field in the parallel direction with this top and bottom plates. Then before the threshold, we cannot disturb the layer structure. It is flat state. But when above this threshold, its undulate occurs. So this is the just schematic picture for that, and this is experimental picture done by Ishikawa and Lavrentovic in 2001. Experimental picture of this, and then so we are gonna, in order to understand this phenomena, we are gonna add this magnetic energy into our free energy. So this is the last piece of my free energy. This is the previous work, the popular classical Helfrich-Hurauer theory, and what they use is the small disturbance from the flat layer state. So, and then they are identifying, approximating n, this which is the director, but in the smectic A, it is perpendicular to the layered structures. So they are approximating this, and then instead of complex order parameter and the director, they use only one parameter u, small disturbance from the flat layer state, and then this making ansatz, and then find the critical field and the description of the undulation at the critical field. So that is the previous work done in 1970s, I believe. And then, but there is a discrepancies between that classical theory and the experiment done in 2000 by Lavrentivic in 2001. So in this experiment, they found the lower critical field, lower threshold, and then larger layered displacement. So amplitude should be bigger than the expected in the theory. And then displacement of layers immediately adjacent to the boundaries, that's not zero. So we should, and the weaker dependence on the vertical profiles. So it's almost like the same amplitude all the way from top to the bottom. So this is that differences between the experiment and the theories, the classical theory. So the later and Lavrentivic, they changed the model. So instead of imposing the strong anchoring condition, they included this surface energy, popular surface energy, to impose this weak anchoring condition. And then it turns out that, but they also approximate this director by this quantity, and still then this experimental result, and the result from this weak anchoring condition model that agrees quite well. But we want to keep our energy right there because one reason is that well above the critical field, my simulation shows that this n is not perpendicular to the layers. So we want to, we don't want to identify this director and the perpendicular direction of the layers. So we want to keep both in our free energy. So this is my free energy for the smectic A, and it's a two-dimensional case, a rectangular domain. And then we make this non-dimensionalization of this. So this is the basically free energy that we worked on, and of course away from that phase transition, making this transformation. And then we can see that this is the undeformed state. So this is the trivial flat layer case. From theta is the angle sine from the director. So in order to define this critical field, we do have the second variation of the energy, free energy, and then we define the critical field that way. So infimum of that minimize this linear functional, then we can find this critical field. And for this lateral side, we impose the periodic boundary condition on the lateral side, and for the top and bottom plate, we impose a strong anchoring condition, but we are going to impose two different boundary conditions on the layers. So I'm going to talk about that in a minute. In order to have the simpler form of the linearized energy right there, so we make another transformation like that, then it will give us the simpler form of the energy. So this energy becomes like that. This is the imaginary part of phi. So obviously it will be minimized when the imaginary part becomes 0. So now we can assume that we can just drop this term, and then we can assume that this phi is a real valued function. So now and then we can capture that small epsilon, small parameter epsilon, so that we can use the gamma convergence theory with this small parameter. So this making this a transformation there. So that means we want to have kind of the unit with rectangle. So we have a little bit long rectangle. So this is the R is a little bit bigger number than 1, but it's order 1. And then with this transformation, we have tau from sigma over epsilon. This epsilon is the lambda over d. So this is from the phase transition term. So lambda over d, lambda is the order of the layer thickness. So what we have is a layer thickness over the cell thickness, sample thickness. So this is a very small number, so that's what we use. And in the first result, we proved that this is order 1, and then what we wanted to do is that we want to have the sharper estimate on the critical field and have a better understanding on the undulations. So we use a Fourier series for thanks to this periodic boundary condition. So this is the one-dimensional one-dimensional energy with a simple notation. So delta epsilon mu squared. U is mu phi. So mu is that phase from the phase transition. Fourier series. So with this one-dimensional energy, once you understand this minimizer of one-dimensional energy, then we can use it to understand, to have this bifurcation analysis. So first we prove that, of course, this is invariant under that sign change. And then we prove that this minimizer is doesn't change sign, either positive or the negative on the interval. And then we define these two function spaces. The first one is the natural boundary condition, so we do not impose any boundary condition on the layers at the top and bottom. But for the Dirichlet case, this is that when U is 0, that means you have that flat layers at the top and bottom in the second case. So it's kind of you enforce that boundary condition that gives the same result as we have in from the Helfrich-Schroth theory. So basically, we look for the minimizer of these functional in these two different function spaces. We do have a constraint, so this is L2 norm is 1, and then the first we use the gamma convergence theory. The gamma convergence theory is that if you have this functional depending on epsilon, and once you prove that this functional itself gamma converges to this functional f naught, then we can just look for the minimizer of f naught, and then we just have a pretty good idea of the minimizer of the f epsilon. So that is the gamma convergence theory, and this is the definition or the condition to prove the gamma convergence. So first, the lower bound inequality. So whatever sequence you choose to approximate u, then in the limit, that alpha epsilon of u epsilon is bigger than the gamma limit. But this gamma limit, choice of the gamma limit has to be sharp. So there is always u epsilon that this inequality becomes the equality. So this is the sharp estimate, and then it always paired with the compactness result. Then once you prove these three types, then three conditions, then we can say that subsequence of the minimizing sequence that is the minimizer of this f epsilon. So we do this. Sorry?
How much does it depend on the class of functions in the
so it depends on function spaces. So it's kind of a critical to determine, I mean, not my case, but kind of critical to determine the function space, because if you have a larger function space, then it's going to be harder to prove this lower bound inequality. But if you have these small function spaces, then it's going to be very hard to prove the compactness. So you have to choose the right function space to prove the gamma convergence.
How do you do it?
My case, it is so it's the phase transition case. So there are lots of previous works, and then this phase transition case, people use bounded variation function space. But my case, it is even though we have two function parameters, so the function space is easier in this case because we do have a good first derivative there. So we just choose L2 or W12 in here, but in the more subtle cases, you have to use the different or difficult cases. Okay, so here, this fixed layers alpha epsilon. So in the Dirichlet boundary condition case, we prove that this is the right gamma limit in the function space like that. And then the general case, the natural boundary condition on the layers, then we do have this different gamma limits. So we have this kind of surface terms that's exactly the linearized term of the Rapini-Popula surface energy. So this is the connection between this gamma limit of our model and the weak anchoring model with the weak anchoring condition. So here, And then once you have this gamma limits, then of course find the minimizer of the gamma limit for each case, then you can have these results. So fixed layer case, this delta is absolute mu squared. The mu controls that frequency. So frequency is like it's a mu squared. The mu frequency is like pi over 2. But in the general case, that goes to 0. So we have a lot smaller frequencies there. And then this function value was pi with this divisional boundary condition. Then it goes to 1. So that critical field becomes a lot smaller with this natural boundary condition. And then this vertical profile, that is a cosine function. So that is exactly the Helfrich-Rault result. So we have a maximum undulation in the middle of the cell, and then the cell thickness is -1 to 1. So that goes to 0 as it approaches to the top and bottom. But in the natural boundary condition, that vertical profile becomes a constant. So that means we do not have the dependency on the vertical profiles of the undulations. So this is just the theorem combined together with the both boundary conditions. This is the result from the gamma convergence theory with this minimizer of this gamma limit for each case. And then this is the table to compare both the cases. So this, as I said before, the fixed layer case, critical field was pi, and then it goes to 1. We could lower that critical field, and then period was the order of square root of epsilon, and then it becomes order 1. So period becomes larger, vertical profile becomes constant, and amplitude becomes larger. So those are the results that we could obtain from the gamma convergence theory, and also actually from that linearized the eigenfunction. So we try to find the eigenfunction because we want to use that for the bifurcation theories. So here is the eigenfunction with this here. So this is kind of the comparable to that result from the gamma convergence theory. The thing is, for the natural boundary condition, it was harder to find that eigenfunction, and we actually used that result of the gamma convergence theory with this for the asymptotic analysis on these eigenfunctions. And then this is the numerical simulation. Just a numerical graph for the eigenfunction that I found. So when epsilon is 0.1, so that means epsilon was the ratio of the layer thickness to the cell thickness. So if that is not too big, so it's more like a cholesteric lamellar system than a smectic liquid crystal, then we're going to have this type of the vertical profiles. So this red one is for the directors. So we force the zero boundary condition at the top and bottom cells. So it has to be 0. But these layers, we do not force any boundary condition on the layers, so this layer can be like this. But still, you have a weak dependence on the vertical. This is not constant yet because epsilon is not small enough. But epsilon becomes small enough, then you can see that this vertical profile of these layers becomes just constant, and then this directors just becomes 0. They kind of have the boundary layers because of this boundary condition. So this is just a simple result from the bifurcation method. We prove that the eigenfunction corner of this linearized functional is one-dimensional, and then we prove that this above this before the critical field, only that flat state is stable, but as soon as it is bigger than the critical field, then that becomes unstable, and then instead non-trivial solution becomes a stable solution. So this is the bifurcation. We prove that this is the critical field becomes the bifurcation point for each case, each boundary condition. So for now, we are going to talk about. I'm going to talk about this numerical simulation. So this is the simpler case first. This is the constant layer density case. In that, we have this gradient flow of the free energy. We have this term that is just a alternative expression of the model with this Lagrange multiplier. So, but we write that way because it kind of resembles the Landau-Lipschitz free energy in micromagnetism. So we could we use the projection method to have this constraint. So that's why we write this way. And then a boundary condition, we have two different boundary conditions on the layers, and then the method that we use best Fourier transforms on the lateral side, semi-implicit finite difference method, and then projection method from the micromagnetism. So then we can we numerically simulate that, and then analysis, we predicted that was pi for that critical field with the divisional boundary condition. So in this case, we are kind of have this larger domain instead of unit domain, so that's why this critical field becomes pi over the size of the width. So this is at 0.25. We don't have any undulations yet because our analysis predicts that this critical field becomes 0.252, and then we see that some undulations right above that. So this is the undulation phenomena, and then this simulation kind of agrees with the result from our analysis. In the general case, we could find that critical field was, instead of pi, it was 1. So again, in this big domain, it's going to be 1 over the thickness of the domain, and then it is like a 0.08. So at this, we do not have any undulations, but right above that, we start to see that undulations, and then you can see that this undulation amplitude is a lot bigger, and the frequency is bigger. So this is what we have with this natural boundary condition. The gradient flow, but we are more interested in that gradient flow with this non-constant layer density. So in that case, we are going to have this phase transition term there, and then boundary condition on the top and bottom. We do have divisional and the natural boundary condition, and then we have those things. So now I want to show that this experimental picture done by Lavrentovic's group. So it's well above the critical field in two-dimensional case. They expect what they have is z-dependent vertical dependence becomes negligible, except that boundaries, top and bottom boundaries, actually at the top and boundaries, that layers join the boundary discontinuously and form array of dislocations. So that's what we exactly have with this divisional boundary condition. So fix the layers on the boundaries, then you can see that this blue spots, that corresponds to that psi is equal to 0. So that means that layer density becomes 0. So we do not have that layer density psi becomes 0 at the boundary of this cells. So and then, but for with this natural boundary condition, we do not have that because of course these layers we have this kind of the form of dislocations. I will show this the director profile in the next picture. But we do have this because the vectors are fixed at the boundaries, but the layers cannot. The layers are the flat in the top and bottom as well, so they cannot match. With this, but the directors wants to parallel to the critical direction of the magnetic field. So that's. But in the middle, we can just have layers can be vertically aligned, so like that. But for the general case, since layers can move freely, we can just go, layers are going to be like this. So that's why we do not have that psi becomes 0 at the top and bottoms. And this is a director profile, so we have this kind of directors changes rapidly around those top and bottoms with this dirichlet condition. And then this one is the general case. So this is, it does not, it's not clear. I just draw that for every 16 vectors, but it does not change that rapidly as we saw before. And now Chernobyl-Lubansky smectic energy. So basically what I wanted to say about Chernobyl-Bansky energy is the numerical new numerical formulation to solve it. So this is that Chernobyl-Bansky energy. What's the difference from the smectic A energy is these two terms. So for this one is the second derivative of the psi, like that, and then this is can be positive or negative depending on smectic A or smectic C, and then this term is the additional term, especially important that when you have a smectic C case. And away from the phase transition, this is the energy, free energy that we have, and then you can see that when the C-perp is negative, so everything is positive, then of course this one wants to be 0, so that's when the grad phi is parallel to the director. That's exactly smectic A energy. And when C-perp is positive, so this term is negative, then you can just combine these two terms together and then find that angle between that director and the perpendicular of layer perpendiculars. So then this angle should satisfy this. So that's exactly smectic C energy. So then we do the same thing. We do the dimensionless free energy, and then capture that the epsilon. So this is again the layer ratio of the layer thickness over the sample thickness, and we do the same type of this is the dimensionless free energy, and then we do the same type of these undulations, the gamma convergence theory, and the bifurcation analysis. So instead of this previous term, so we have additional term, and then in order to prove gamma convergence for this case, so we have to kind of smooth that sequences, because now we are in the H2 space, but in this targeting space is H1. So we have to smooth out these approximations. But this is done, and then we can have this bifurcation analysis as before. So again, we prove that existence and the stability of the non-trivial solution curve above that critical field for each case. Now I want to go to this numerical formulation now. So the gradient flow equation associated with this Chernobyl-Bansky model is given by that. So you can see that this is, since the free energy has a second gradient, so this the gradient flow has the fourth order differential equation. So in order to simulate the fourth order differential equation, it takes a lot of time, and then it's not simple. So instead, what we want to do is take the gradient flow in H1. So setting U is grad phi, then you can have this. So of course, the second gradient becomes, fourth order derivative becomes the second order derivative, but the price for paying that is that constraint. We do have this constraint now because U is the grad phi, so curl of U has to be 0. And then we just put that into this equation, like the pressure appears as the Lagrange multiplier of the incompressibility condition. So we put that pressure kind of term into that equation, and then this is going to be compatible with this free energy. So so now we want to solve this equation instead of the fourth order differential equation. So in order to solve that equation, this is kind of Navier-Stokes equation. So the method that we used to solve the Navier-Stokes equation is the gauge method. So I want to explain this gauge method for a minute. So we have this Navier-Stokes equation like that. Then the problem when you solve this Navier-Stokes equation numerically is with this pressure boundary condition. So this is the pressure equation, and then boundary condition is like that. So it's kind of difficult to solve this boundary condition because the consistency is between these two. So that's why this projection method was invented to bypass that issue. But this the price for the projection method is they have to use this special discretization scheme to use that projection method. So instead of the projection method, we use this gauge method, which is we kind of introduce that gauge variable and auxiliary field. So that equation this equation becomes like this. So this is like the heat equation and the Poisson equation. And then what's nice thing about this method is that we can freely choose that two boundary conditions for phi, the gauge variable. So we can either choose this Neumann boundary condition or the divisional boundary condition, but it turns out that this Neumann boundary condition is more stable and efficient. So we used this Neumann boundary condition for the gauge variable. We go back to our model, and then note that this is just the Laplace of u plus curl of u, and then the layer structure. And also, of course, we want to find the layer structure. Once you solve all those system of equations, then you can recover this phi by solving this equation. So grad phi was u. So instead, we are solving this equation with the suitable boundary condition. Then we can recover that layer structure like the screen function in the fluid dynamics. So with the gauge method, now our system becomes like that. Still, we are going to use that projection method to have this condition unit vector, and it has to be unit vector. And then we have those 4 equations, but these are all second order, and it's like a hit or Poisson equation type. So we can solving the Navier-Stokes equation is no more difficult than solving hit and the Poisson equation with the gauge method. So we can use that, and our formulation is kind of good, very efficient for if your functional is like a grad psi and a grad squared psi, like secondary gradient. So this is the first example that we did. So if you just consider this Avogadro's smectic energy, then this is the perfect example for us. So it's exactly like this form. Then we can use this perpendicular anchoring condition. Then we have these layers perpendicularly aligned like that. So director is perpendicularly aligned like that. So this is the first example using this method. And then now we use that for our Chernobyl-Bansky functional. So this is a divisional boundary condition case. So we have, you can see that this critical field matches the one that we had before, and then one with our analysis. So this 0.252, that was the critical field. So we have good approximation with that, and the same oscillations, the same frequencies, and the same critical field. And above that, I know that it is not that physical because we are using the constant density case in the Chernobyl-Bansky functional. So, but this is what I have for now. And this is the TOEI problem. So this is the smectic C. We do have only 2-dimensional domain with this formulation because one difficulty is that when you put that constraint curl of u is equal to 0, now in the 3-dimensional domain it becomes the vector instead of the pressure term is not a variable, one variable, it becomes the vector. So that's what kind of gives the difficulty. So this is the smectic C. So we just put that different boundary conditions aligned in like a minus 20 degree over here, top at plus 20 degree for the angles. Then first, of course, we do have a little bit of kind of this weird shape because if this flat state is not the critical field with that boundary condition, but a little above that becomes flat, but we cannot explain that. And then we see some undulation types. But this is a 2-dimensional domain for smectic C, so it's just a TOEI problem. And then we do this asymptotic analysis to understand that to have this numerical simulation. So to match with our numerical simulation. So well above this critical field, this is our asymptotic analysis for the layer and the director. And then this is just a 1-dimensional asymptotic analysis in the real line. And then this profile actually kind of matches what we have from the numerical simulations. So this is that asymptotic solutions. So from this, so you just graph these asymptotic solutions. And then this is the picture from our numerical simulation from the Chernobyl-Bansky functional. And then they have a good agreement between these two. Now, finally, I like to talk about this three-dimensional linearized, three-dimensional functional. So for this one, for the three-dimensional case, instead of applying the magnetic field in the x direction, we apply this z direction. And then this diamagnetic anisotropy becomes negative. So instead of directors parallel to the magnetic field, it wants to be perpendicular to the magnetic field direction. So in here, we do this because if you just apply the magnetic field in the x direction or the y direction, it's not that interesting. It is just the same as the two-dimensional case. So that's why we have this. So this is that vertically applied magnetic field. And then with this constraint n equals 1, this is the magnetic energy that we use. So with that magnetic energy and free energy, we non-dimensionalize it. And then with that one, since it is a three-dimensional, we didn't want to use this angle notation. So we just stick with that weak formulation for the critical field that was given by Hwang and Sigmund Pan, or in the previously Loskins. So we use this form of this weak critical field, and then this is, after that, if you find this Fourier series for that, and then solve this one-dimensional problem, then you can manage that to find that critical field and the oscillations and everything. So once you find, what the thing is, you can find that actually this critical field is the same as before, and then frequency is about half that frequency you have in that two-dimensional case. Conditional boundary condition. So this is the square lattice type of the undulations. So I have a flat layers. This is just for the visualization. We have just in the undulation just in the middle of the cell. So first, we do not have any undulations, but as soon as it reaches that critical field, you are going to see that undulations. And this is that little bit bigger undulations, a lot bigger, but you can notice that the period becomes bigger when you increase that magnetic field. So director configuration shows the same thing. So you can see that this undulations on the x direction, y direction is just the same as before for the two-dimensional case. So this is the square lattice type. But what we are more interested in this with the numerical simulation is the profile well above the critical field. So here is the experimental picture, again done by the Lavrentovic, and then this is the axially symmetric domain appears at 1.9 of the critical field, and then what we have is near the critical field. This is the section of that undulation. This is the XZ section, and then this is the YZ section at the critical field, and then it becomes bigger. Then you can see it's just the kind of undulation is bigger in just one direction. So this is the undulation numerical simulation that we have. This is a YZ direction. This is still same. But in this XZ section, we have this peaks of the undulations. So that's what we have here. And then if you can see this, this is something that I wanted to point out. So this is the layers, and then this is that density, the contour map of the density of the layers. So you can see that this, these is the regions, this is almost 1, the density is almost 1, but it becomes smaller inside of this kind of the flat layer state, because that is the flat layer state. You can see that directors are kind of not parallel to the layer normal direction. So even though it's a smectic A phase, but still this director is kind of skewed away from the layer's normal direction, and then density becomes smaller in that state. So this is but the other section is just the same as before. So we can see that this is kind of the undulation shape in a two-dimensional case like that. So this is now the natural boundary condition. We have the same similar thing. So flat and then bigger and bigger undulations. And the one thing that we kind of observed is that we know that layers well above the critical field. Experiment shows that this square lattice type undulation, it transforms to the 1D stripe pattern. So that's what we obtained here. So well above this critical field, that undulation becomes like that. In one section, it is just the flat layers flat, and then the other section we have undulations. So it just picks the one direction of that undulation produced. So this is the simulation that we had for three-dimensional domain. We are still working on this three-dimensional case for the bifurcations, but we do have we understood the linearized model though. So that's what I have. Thank you very much for your attention.
Thank you very much for your presentation. I would invite questions now.
I was going to ask, how does it choose one direction or the other for the stripes?
I don't know. But in your paper, it's that it just is there any particular direction that undulation chooses?
No. Like,
So if you compare the ratios of the different thresholds, like the Helfrich Hero threshold and then the threshold of the stripes, do you have a consistency with the experimental data?
I didn't do that quantitatively comparison. Yeah, I will.
Tim, please.
When you turn the field off, what happens if you go into the high field regime and you set up dramatic stripes? What happens when you turn the field off? Does it just in your numerical scheme? Does it go back or does it remain with a structure?
I haven't tried, but we could probably we could manage to see how it shows numerically.
Because this is actually interesting because people make bistable devices sort of this way, not using this basic general idea, and it would be interesting to see whether or not what you put in is sufficient to give you a bistable, or whether or not one needs something extra on top of that.
And so you turn off and then switch the direction.
You turn on the field, and you distort dramatically, and all of the presumably interesting things are now happening close to the boundaries rather than. And now you turn it off again, and you see whether or not the system is able stably to return, and it may or may not. Experimentally, under many circumstances, it does.
Experimentally, is it done then experimentally?
Using electric fields, and at low frequencies, so that it's driven by dissipation rather than by dielectric effects. But same sort of general idea.
For smectic A,
For smectic A, yeah.
Very interesting.
any further question? Well, apparently no. Then we thank again our speaker.
Thank you very much.